Section 12.1 Vector-valued functions. Section 12.1 Vector-valued functions. In this section, we are going to see how we can describe curves in space. So this is different from what we did in Chapter 11. In Chapter 11, apart from lines, we studied surfaces. So when we want to describe a curve, which is a one-dimensional object, we are going to use vector-valued functions. This is here an example of a vector-valued function in the plane. And here's an example of a vector-valued function in space. So you can see that it is a vector, and the components of the vectors are f of t and g of t. So if you know that f of t is 3 and g of t is 5, then the function points to the vector 3, 5. 3i plus 5j. What this means is our vector-valued function is going to be a vector that always points to a certain point on the curve in the plane or in space if we have an extra component. So these components, f, g, h, etc., if you were in more than 3 dimensions, are called the component functions. So you choose a certain value t, it spits out f of t, g of t, and h of t, and that's a vector. So we are focused on the head of that vector. The tail of the vector is always at the origin, and we look at where the vector is pointed. All of the places that the vectors point creates a curve. So when t increases, the vector is shifting its position and it's kind of spanning the curve itself. If it happens that f of t, g of t, and or h of t have limited domains, then of course the curve won't be defined at points where one of these is undefined. So if f of t has a limited domain, it doesn't matter what g of t and h of t are, the curve itself will be limited by f. The domain of a vector-valued function is the intersection of the domain of the component functions. So you will only have a curve defined where all of f of t, g of t, and h of t are defined. Here's an example that's going to show us that actually vector-valued functions are not something very difficult. The vector-valued function r of t is cosine ti plus 3 sine t j. I think it's a 3 here in your notes. This corresponds exactly to the parametric equation x equals cosine t. I just took the first component function, and y equals 3 sine t. I took the second component function. And this is always going to be a correspondence you can trust. It means that the point xy which we are expressing here is expressed as a vector where this is x times the first standard unit vector plus y times the second standard unit vector. Now that we've written the parametric equations, we may realize, oh, this is just an ellipse that has x-intercepts at 1 and -1 and y-intercepts at 3 and -3. So what does it look like in 3 dimensions? It can be quite difficult. Here's the answer, so it doesn't seem like it may be so difficult, but let's try and look at the vector-valued function itself. X is 4 cosine t, y is 4 sine t, and z equals t. The first thing you may want to try doing is plugging in some values. So if we look at this and we choose t equals 0, we will get x equals 4, y equals 0, z equals 0. This is the point that's written there, and it corresponds to the point right here. We could try another point, and because I see cosines and sines, choosing t equals 1 might not be the best idea. Maybe if I choose t equals pi over 2, it's going to give me a better point. If t equals pi over 2, I get 4 cosine of pi over 2, which is 0. Here, 4 sine of pi over 2, which is 4. And z is equal to pi over 2. So I get the point 0, 4, pi over 2, which is that point right here. So this might help us. We now have 2 points, the point down here and the point that is in the YZ plane. But from then we may want to think a bit more holistically about these three equations. And notice that if we were not in space, then x and y would define a circle. So the graph is going to be a circle. When t increases from 0 to 2 pi to 4 pi to infinity, it's just a circle that is turning and turning and turning on itself. But while this circle is being drawn, we have an extra component, which is z, which is rising slowly. So as t increases, z increases, and so the circle that is turning and turning and turning is now turning, but going up at the same time. So the point here, for example, corresponds to t equals 2 pi, the point here corresponds to t equals 4 pi, and so on. This is called a helix. By the way, it would also go down to the left of this point. Of course, it would kind of curl down as well. How can we represent a vector-valued function if we have a regular standard equation of a function? I think it would be a good idea here to add to this sentence and say that we are in the plane, just so that there are no confusion, because we're jumping between 2 and 3 dimensions. So use a vector-valued function to represent the parabola y equals x squared plus 1 in the plane. Nothing's easier than that. In fact, what we do is we just choose x equals t, and then that binds what y is. Y is now equal to t squared plus 1. So from our parametric equations, we can just write the vector-valued function itself. R of t is t, so the x value, times I plus t squared plus 1 times j. Lastly, for this section, an example that looks extraordinarily complicated. We are looking for the curve of intersection of the semi-ellipsoid, so it's this eggshell that we can see, this dome, if I can say. We're looking for the intersection of that and the parabolic cylinder. The parabolic cylinder, we can vaguely see it, it's inside. The parabola is here, and then it would go up, and it would, of course, extend beyond the semi-ellipsoid. But in order to see the curve of intersection better, it was not sketched. So a vector-valued function will be an arrow that points here, and then as t increases, the vector will point here, and then the vector will point there, and then the vector will point here, and so on. So the head of the vector will travel along the curve. How do we do that? Well, we know that this curve is always entirely included in the parabola. So if we say x equals t, it forces y to be t squared thanks to this expression here. So x equals t, therefore y equals t squared. And because the curve, the black curve that we are looking for, is also entirely included in semi-ellipsoid, we know that it has to satisfy this equation for all its values. So we can substitute x equals t, y equals t squared, and then solve for z. And that is how I got z equals the square root of 4 times 1 minus t squared over 12 minus t to the 4th over 24. So in conclusion, as a vector-valued function, we can write that r of t is ti plus t squared j plus this square root times k. So that concludes section 12.1. And for the next sections, it's going to be self-guided with your notes for the last page. Thank you.